Okay, we'll go ahead and get started. Just a quick announcement. The syllabus page in Canvas now has a downloadable Excel file that you can use to calculate your grade. So you just enter your points and it'll calculate your grade sort of in real time according to how many points have been available so far. So just scroll down below, like where the exam scores are posted, you can get that Excel file. If you have any bonus points, just add them to your exam and it'll spit out the correct letter grade for you. Any other questions before we get started? Yep. Just add them to any exam, just as long as they're, the exams are out of 60. Whatever bonus you have, just stick in those columns as part of your exam score, and it'll calculate it based on some functions there. So we had left off with the synthesis of alcohols from carbonyls using the hydride reducing agents. So there was sodium borohydride, which only acted on aldehydes and ketones, and then lithium aluminum hydride, which acts on all oxidation state 3 functional groups. So what if we want to make a tertiary alcohol, or what if we don't want to use hydride reagents? What's the alternative? These are organometallic reagents. So this word is just jammed together of organic and metallic. So really what they are carbon anions or carbanions. So we're going to look at the carbon bearing an OH group, and then we can think about what carbonyl groups can that come from. So that's called retrosynthesis. So to preface this discussion, if we think back to Organic 1, we learned about bonding and changes in electronegativity and what a covalent bond is. There's sort of two types. There's nonpolar. So nonpolar, those were your typical CH and CC bonds. And then as you substitute out for heteroatoms, you get these polar covalent bonds. And, in general, they're polarized because of the electronegativity, but also these lone pairs. And we can assign that delta plus to the carbon, delta minus to the heteroatom. So the polarity of that bond is carbon is delta plus. In a carbanion, the carbon is formally negative. So how can we switch the polarity from its how it normally is based on the heteroatom to being the complete opposite to make a carbanion? So stated another way, these carbons are electrophilic. And we want to make them nucleophilic. So in terms of the logic, we have to switch the polarity. So organometallic reagents, you can think of them as this form, M+, that's a metal cation. And then X is the carbon bearing a lone pair, and it has a formal negative charge. So it's like an ionic salt that you've learned from Gen Chem. So we'll see what metals are typically used, and then how do we generate these carbanions. And so within that, the carbon atom can be sp3, sp2, or sp hybridized. So we can make any carbanion based on the hybridization and then going back to all the functional groups we've learned. So what are the hybridizations and the functional groups? So if we want an anion where the carbon is sp3 hybridized, we start with an alkyl halide. If we want sp2 hybridization, this is an aryl, so that word means aromatic. Or if we want sp, we have to start with a terminal alkyne. So that means of the alkyne, one of the sp carbons has an H bonded to it. In terms of the rate of the formation of these things, especially for these two right here, typically you want the halide to be iodine, bromine, or chlorine. This really does not work for fluorine, or at least no one's figured out how to do it yet. So that's the trend. Iodine is better than bromine, is better than chlorine. You can use any of the group 1 metals, so lithium, sodium are probably the most common. Potassium is used as well. As you go down that group, those metals get more reactive. So really it's a balance between the size and reactivity of the M+ versus the carbon anion you're trying to generate. So you can use group 2, magnesium. So those end up being magnesium 2+. And so since it's 2+, you'll either have sort of 2 of the carbon anion substituents or 1 plus some other ligand to balance the charge. And now, as opposed to the hydride reagents, the solvent is very important. They have to be aprotic solvents. So a carbon anion it's a very strong nucleophile, but it's also a very strong base. So you cannot have any acidic protons in your solvent. If you do, acid-base reactions happen at what's called diffusion. They happen the fastest. So that will happen first and essentially quench the reagent you're trying to make. So the appropriate solvents, so there's alkanes. So toluene, again, is methylbenzene. Diethyl ether, or tetrahydrofuran is just diethyl ether in a ring. So when you look at the functional groups present in there, the pKa's of those are all really high. The CH bonds are not very acidic. So to put that another way, you cannot use things like water or alcohols or amines that have OH or NH groups, because those will effectively do acid-base and quench your nucleophile. So this is a summary slide of how these are made. And really what I want to point out is I'm just picking some examples. Really what you're focused in on, where is the action happening? Like here I have 1, 2, 3, like a 4-carbon chain. This can be sort of anything, as long as that's sp3 hybridized and that's a suitable halogen. The rest of this is whatever the molecule needs. So with the sp3, so again, we can assign the bond polarity like that, just based on the difference in electronegativity. So the carbon's electrophilic. We want it to be nucleophilic. So it turns out that if you take lithium metal, so two equivalents of that, and notice the solvent is hexane, so it's inert. You take the bromobutane, dissolve it in hexane, and add lithium metal. And what's interesting about this is lithium metal it's like a silvery looking, it comes actually in a wire, you can snip it with scissors. It's a solid, you're adding it to organic stuff, and it will eventually dissolve. So that's interesting to think about. You have this non-polar solvent, and then this metal is dissolving it. So what's happening is this lithium 0, that just means, lithium has that valence electron. It's giving it up. And the reason you need two equivalents of it or an excess is that so you can invert the polarity of the bond. So I'm drawing the molecule like this with a bond. So normally you think that's a polar covalent bond, but the better way to think of it is now that that carbon owns the electrons in the bond. And so in a sense, it is ionic. It's carbon minus lithium plus. So that's that form M plus and then X minus. And so that's called N-butyllithium. N means normal, or one position. So depending on where you generate the carbanion on the chain, they'll have different sort of prefixes. But the take-home message is wherever you have that alkyl halide bond, you can treat it with metal, and it inverts the polarity. So organolithiums are sometimes called Gilman reagents. So for an aromatic or aryl halide, so that carbon is sp2. We can assign the partial positive, partial negative like that, again, based on electronegativity. Now in this case, when we're using magnesium 0, magnesium ends up as divalent. So notice in the product here, you have the carbon anion part, but then you also have this bromine substituent or ligand. So this could also be drawn as like Mg2 plus and then Br minus, where this negative and that negative balance off that 2. And so organomagnesium reagents are called Grignard reagents. So Grignard won a Nobel Prize for figuring this out. Have you guys done your Grignard reaction in lab yet? You'll take a compound called benzophenone. You'll probably take bromobenzene, make the Grignard, and then make an alcohol. And it probably won't work. Because the issue is, as I said, this is fine. It's a liquid in a bottle. This process is tough because one, the metal has to be activated, because what it's doing is it's essentially inserting into this bond. And once it makes that carbon negative, that's like super reactive. reactive so much that, like when you breathe in, there's moisture in the air. Like that moisture will quench that. So once you form that and you add your substrate, you're going to get, if it works, you'll get a pretty low yield. Just because those things are so reactive, and then the labs you guys do, you don't take a lot of precautions to exclude moisture and oxygen and things like that. So that's an sp2 hybridized carbon anion. Yep.
I'm just confused at how it goes from partially positive to that negative. Like what are those electrons?
So like in this nomenclature, that just means like magnesium in its just normal state. So like elemental magnesium will have 2 electrons. So the mechanism by which this happens is kind of complex. But those electrons insert into this bond.
Because the plus is positive?
Yes. So notice it's this CH bond, it's not polarized. It doesn't care about any of those. This is the only different one. So that metal, as you run this, it also starts dissolving and disappears. So it inserts into there. And that's what flips the polarity. So again, you could take this bromobutane, treat it with magnesium, and then you would get the Grignard of this. So these are just some examples to highlight the reactivity. For the sp hybridized carbon, again, you have to use a terminal alkyne. So you need that acidic CH. And so you treat that with a base, sodium hydride. And that just does an acid-base reaction. And so now you have the sp hybridized carbanion plus the sodium cation to balance off the charge. So we'll spend time today applying these things. And how do we make different alcohols from carbonyl groups? Then we'll have a slide where we're just looking at an alcohol and then determining the ways in which we can make it. So to give you a preview of that, anytime you see an alcohol, regardless of what it is, there's 3 ways you can make it. Any questions? Yeah.
So you said like in like the aryl halide on the left, that like you can bottle that, it's stable in a bottle.
Yeah.
When you add the magnesium, is like the charge different? Like it's more negative on the carbon, and that's why it's reactive, or is it like equal amounts negative and positives?
I think for this class, the best way to think of it is that carbon has a full negative charge. And then the magnesium, the way this is shown, the magnesium is going to be your plus. So it's like that salt form. So that will help you think about the reactivity. So we'll draw some arrows on the subsequent slides so that you see where the nucleophile is originating. So again, due to the constraints of how things are taught here at USM, your exams are online. When I was a graduate student helping administer exams, all the exams were free answer. And so during that, students would have to write mechanisms. And a lot of times they would show arrows originating from something positive. And again, that violates the convention of how the nucleophiles are attacking things. So we'll do some of that just to clarify any misconceptions about how you match polarity, because that's the sort of the logic we want to follow. in terms of looking at a complex structure and making it simpler. So we'll run through these primary, secondary, tertiary, and see how we can apply these organometallic reagents. So this exercise, we're calling it a disconnection, or the term we use is retrosynthesis. We have a primary alcohol, benzyl alcohol. That's what we want to make. And what can we make it from? So that's the carbon bearing the alcohol, and I've traced it all the way back. So we essentially want to make that bond. So in thinking backwards, we can break it just based on polarity arguments, where the starting carbonyl group comes from formaldehyde. So see these two H's? Those H's would come from formaldehyde. We know that the carbonyl has that polarity. And so the organometallic reagent we would use is this sp2 hybridized carbanion. So this, again, this type of arrow means retrosynthesis. That's our blueprint for the plan of work we want to do. Then in the forward direction, we would make the organometallic, we would quench it with formaldehyde, and then in the workup, we would adjust the pH. So how does it look in the forward direction? So the Grignard reagent is called phenyl magnesium bromide. You can actually buy these things. So they come in a bottle. The bottle has a rubber septum on it. You know, like when you get a flu shot and they stick a syringe in the vial, they're piercing a rubber septum to keep it sort of aseptic or whatever. That's essentially what these reagents come in, except the bottle's bigger. You take a syringe, you measure out your volume, and then you use it. But as we saw, you can just make this from the bromobenzene with magnesium, metal, and THF. So that's how we would make that. And so we have delta minus, delta plus. Magnesium is plus, this carbon is minus. And then the logic of this is you're just matching the functional group polarity. So the negative is attracted to that positive. We break the pi bond, and those electrons go on oxygen. And so the reaction doesn't complete. It sort of sits at this stage. And we called that an alkoxide intermediate. So it sits there until you do this, the workup. And so what you're doing there is you're just adjusting the pH to protonate that oxygen. So in a proton transfer with hydronium, it would look like this. And then you would end up with your, in this case, primary alcohol. Question?
Yeah, why does that carbon have, a lone pair? Because it's got, like, the correct number that it likes.
So, you know, if I'm showing it as sort of an actual covalent bond, but in reality, that magnesium would be plus, and this carbon would be minus. So this sort of drawing is just showing you who owns the electrons in the bond. So to thread this to what we learned about on Monday, you could start with benzaldehyde. So that's at oxidation state 2. Treat it with sodium borohydride, and that would do a reduction to get the same product. So again, what we're looking at is when we see an alcohol, what are the different ways we can make it? Questions? So what is the molecular formula of the alcohol formed when propyl magnesium chloride is treated with formaldehyde followed by acidic workup? So this is our organometallic. This is our electrophile. And we want to determine the molecular formula of the product produced. So propyl is 3. So propyl magnesium chloride plus formaldehyde. And I'll say then acidic workup. So maybe we can answer this piece by piece. How many total carbons should the product have? 4? So that would eliminate A. How many total hydrogens should it have? So I'll give you a clue. It's got to be an even number, so we can eliminate 11. So now we're between 8 and 10. So we can count. There's 3, 4, 5, 6, 7, 8, 9, and then that's going to get protonated, so 10. So we would end up with C. When we draw the mechanism, the carbanion attacks the carbonyl. We break the pi bond. And then the acidic workup will protonate. So we would end up with that alcohol. So 1 butanol. questions? So formaldehyde is a nice source of one carbon atom. Another electrophile that we can use is called ethylene oxide. So ethylene oxide is an epoxide, it's a cyclic ether. And it's a nice reagent to use to form primary alcohols that have a CH2 spacer. So the same logic is at play here. Oxygen's delta minus, either carbon atom is delta plus. And the reason this is a nice reagent is because of the ring strain. By opening the ring, you reduce that strain, and so it's a good electrophile. Experimentally, the only pain with using it, it's a gas and you have to condense it. So in the forward direction, say we have phenyl magnesium chloride. We can see again that carbon is minus, the magnesium's plus, so we match up the polarity. That will attack the carbon, the ring will open, and then we adjust the pH to acidify. And again, you end up with a primary alcohol in that case, but now you have that linker. So I'll highlight that in blue. So see these two carbons? Really, you're looking for that pattern. So when you see CH2, CH2OH, you can say, I can use ethylene oxide to make that. Any questions?
What would ethylene oxide look like after that ring is opened up? Where would the magnesium chloride like attack the oxygen?
So the intermediate for that?
Yeah.
It's going to balance off the negative charge of the oxygen. Okay, so say we want to make one hexanol. So we're gonna think backwards now. So that's one hexanol. And we want to make that using ethylene oxide as the electrophile and then one of these as the nucleophile. So this has 6 total carbons. Ethylene oxide supplies 2 carbons. So based on that information, which Grignard reagent should we use? The 4 carbon chain, so B, butyl. So if I dissect the molecule between carbons 2 and 3, I can say that carbons 1 and 2 come from ethylene oxide. Three, 4, 5, and 6 will come from the Grignard. So overall, that Grignard is supplying 4 carbons. So whenever you're given like a product, what you're trying to do is simplify it to less and less number of carbons.
And do you know we have to use the ethylene oxide or formaldehyde? Because both of them give us primary alcohol.
Yeah, so I mean, another way you could do this, so maybe I'll draw it in green. So that's one way. Say you wanted to make that bond. And so in that case, you would start with formaldehyde as your electrophile, and then you would have a 5-carbon Grignard.
Yeah, nice.
So to answer your question about, wait, I think I numbered this wrong. Two, three, 5. Okay, so that looks better. So the question was, how do you know what to pick? That's sort of where we're going with this. You know, conceptually, you want to think of all of the different ways. What are the different nucleophile-electrophile pairs? And then experimentally, if you were going to go into the lab, you would at least have those options. And then what it comes down to is, what are the cost of these things? How much does it cost per each pair? And then how do you handle them? Like, for example, formaldehyde itself is a gas. Anyone work around formaldehyde at all? It really smells bad. I mean, it's not pleasant. So that would be a reason like, well, we might not want to use formaldehyde. Ethylene oxide, it's also a gas, but you can condense it into a liquid. It's a little bit easier to handle. So there's just practical considerations. But for our learnings, we want to understand the logic of this. So with that, any further questions? So what if we want to make a secondary alcohol? And now, again, considering what we learned last time, we know that a secondary alcohol could come from a ketone. So we could take this ketone and reduce it with either sodium borohydride or lithium aluminum hydride. But if we don't have access to the hydride reagents, what are the other ways we can do it? And in the first route here, we're gonna break that bond in terms of thinking backwards. In the forward direction, we'll make it. So we can end up with these 2 carbons right here coming from an aldehyde or ethanal. And then our organometallic reagent would be that cyclohexyl group. So again, the factors of that are what are the cost of these things, the safety precautions involved, and then I think OSHA still exists for now, unless it's been shut down. But when you're working with chemicals, there are safety data sheets, and OSHA has specified what is the maximum daily exposure for things. So they count how much of it gets into the air, how much a human absorbs through their skin or breathes, and they do that testing to see what is the permissible limits of working with such things. Recap, this is two ways. Again, let me highlight the carbon bearing the OH group. So in one way, you can start with a ketone and reduce it. That installs the hydrogen. Another way, you can start with an aldehyde and then put that ring in. And so there's a third way. So in the third way, you would start with a different aldehyde and a different organometallic. So based on that information, what organometallic do you think you would start with? So on the prior slide, we looked at that disconnection. This H disconnection comes from hydride. And then the last disconnection would become from there. So how many carbons does that split off into? One. So if you start with now that aldehyde, because it has the H, it has the cyclohexane ring, we need to add a CH3 group. So this would be B. So CH3, we'll say we're going to use the lithium reagent. So that would be your alkoxide intermediate. So anytime you see that carbon bearing the OH group, there's three ways you can do it. Questions?
Is there a sequence we follow from methyl magnesium iodide with the aldehyde, and then we get that? Is there a sequence we follow?
I guess in terms of like doing it in the lab, typically what you would do is you have your empty flask, you add your solvent, then you would add your electrophile. You probably have to cool it, and then you would add your nucleophile. So you would let it run, and at some point you would say, okay, the starting material has been consumed, and now we're going to adjust the pH. Question?
I'm confused how you get that answer from what you have, because there's no magnesium or iodine.
Well, that's the, oh, sorry. This, I wasn't looking at the full thing. That's just the counter ion. So I drew methyl lithium. So methyl lithium or methyl magnesium iodide are both supplying one carbon. It's just a matter of what the metal is. And again, that choice would come down to cost, like how much, basically the way that I look at it when I'm buying stuff is like dollars per gram. So I'm comfortable buying things that are about $1 per gram. Anything more than that is too expensive. And you can find these things online to see what costs are. So I'm just going to call that carbon that's bearing the hydroxyl, the carbonyl carbon. So it has the OH, and then it has 3 other substituents. So from that, you can come up with 3 pairs on how to make that. In one way, we can make that bond. The second, we can do that, where we're adding hydride. And then in the third, we're dissecting that. So what you're looking at when you draw those lines is you have to include everything that's sort of below the line. So this is the cyclohexane ring, this is the H, and that's just a single carbon, methyl. So that gets back to what I said at the beginning when we were forming those organometallics. You can basically form them from anything. Yeah.
How do you know that the methyl magnesium iodide only provides one carbon?
So, by definition, methyl means one carbon.
Okay.
So here we have a 2-carbon aldehyde, ethanol. Yeah.
I'm sorry, I'm still confused how you found that it was only one carbon on the last.
So if we're going to start with ethanol, so that's the electrophile. Ethyl magnesium bromide is the nucleophile. And the question is asking you, what is the product? So as a clue, the electrophile already has one carbon. You're adding a second one to it. So we can eliminate one butanol. So 2 butanol. So we started with 2 carbons. We're adding 2 carbons through the nucleophile. We have 4 total. And because we're using an aldehyde as the electrophile, it has to be a secondary alcohol. So I know we're throwing a lot of numbers around here. 2-butanol is telling you the location of the OH. Secondary is telling you the class of the alcohol.
What would the intermediate for that look like?
So as a review, so there's the 2-butanol with the carbons numbered. How many hydrogens are attached to each carbon? Yes, so D. So carbon 1 has 3. Carbon 2 has 1. So that gets rid of C, then A. Then carbon 3 has 2 hydrogens, so that gets rid of B. And then carbon 4 has 3 hydrogens. Now, if you're looking to assign carbon chemical shifts, you remember how carbon shifts away from 0 as you add heteroatoms? So the sort of the milestone here would be carbon 2 bearing the OH group. That should have the largest number. So when we scan column 2 and we look at the possible choices, which row or response best fits that? So B. So the 4 numbers are all the same, just in different orders for these. So oxygen, since it's electronegative, it's going to shoot it way past everything else. So that carbon should have the highest chemical shift. And then looking at C1, C3, and C4, you're just doing the additivity rules. So what I mean by that, carbon 4, that CH3 group, it looks the most like methane, so it should be closest to 0. Then carbon 1, it feels a little bit of that tug from the oxygen on carbon 2. And then carbon 3 has 2 carbon substitutions. Any questions on those assignments? So we're up to tertiary alcohols now. So these are unique for a specific reason, and then we'll dig a little bit deeper with the remaining time of today, looking at a tertiary alcohol and what are the 3 ways we can make one. What's unique about tertiary alcohols, and especially in this sense right here, so let me pick a color here. Okay, so I'm gonna call that blue. The carbonyl carbon, which is blue, notice that 2 of those substituents are the exact same. You have 2 ethyl groups. When you have a tertiary alcohol with 2 of the exact same substituents, those can come from an ester. So if you look at what you're starting with, that compound is called methyl benzoate. The reason you can start with an ester that's at oxidation state 3 is because those will do an addition and then an elimination to oxidation state 2, which will undergo a second attack by the Grignard. Does everyone follow that logic? I'll draw the mechanism on the next slide.
Can you repeat that again?
So this is a sort of special case when the carbon bearing the alcohol, if two substituents are the exact same, you can start from an ester. So in the next slide, I'll show the mechanism of why that is. Because overall, we know that there's a tertiary alcohol, it's at oxidation state 1. So using the logic, we can start from oxidation state 3. So oxidation state 1, tertiary alcohol. So that the ester carbonyl polarity is the same. So that does an addition. So that's one equivalent. A couple of things that are important to point out in this that will help us as we move forward in the next module or two. We said the carbon's at oxidation state 3. It's sp2 hybridized. In this first intermediate, what's the oxidation state now? It's at 2. And then what's the hybridization? sp3. So what I'll just explicitly say is that's weird, right? Because when you're used to seeing oxidation state 2, the carbon is normally sp2 hybridized, as in a carbonyl. But now, since it's sp3, what happens is this negative charge on oxygen collapses back down. And when it does that, it displaces the alcohol part of the ester. And so it's going to reform a carbonyl. And so now that's the normal oxidation state 2 you're used to seeing with sp2 hybridized carbon. So you form that reactive thing in the reaction. It doesn't think. It can't control anything. It doesn't chill out and say, leave me alone. The Grignard sees it, and it's going to react with it because it's a carbonyl. So it's going to do another addition. So now we've reduced it all the way down to oxidation state 1. And the hybridization is now sp3. And then we just finish off by protonating with hydronium. And that will give us the tertiary alcohol. So if you plan on going to like biochem, either the baby biochem or the 3-semester sequence, understanding this sort of analysis with hybridization and oxidation state is important, because they'll talk a lot about that in terms of enzyme kinetics. How do the enzymes in your body carry out chemical transformations? And transition state analysis is pretty important for that. Yep.
So the formation of that sp2 carbonyl and that's an intermediate, is that what kicks off that oxygen that's connected to the methyl in the first intermediate?
Yeah, so this, we'll talk more about this mechanism, I think, in module 3, but this ends up being a good leaving group, because that leaving group, CH3O minus, so that's a good leaving group. It's a good leaving group because when you think about the conjugate acid, and relate it to pKa, that's a stable molecule. So you can't get away from the stuff from semester 1. We're constantly bringing it back into the discussion. So again, as I said, that's a unique case when the alcohol has 2 identical substituents. So looking at the product, we have a tertiary alcohol, and we want to use the methyl Grignard. So what starting material should we use? If I color this green, that sort of maps things. Does that help out any? Huh? Thought I heard someone say something. B as in boy?
Yep.
Yeah, that's the right answer. So how did we get that? So that carbon bearing the alcohol has to come from a carbonyl. And then from there, what you're counting. So CH2, 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 there's 3. CH2, CH2, CH2. In A, there's only 2. C, these are the distractor methyl groups. And then D has too many in the linker. So in that prior mechanism, we showed that ester oxygen floating away as like methanol. When you start with this, a cyclic ester, that leaving group, it's tethered to stay in the molecule. So that's what you see at that bottom part, alcohol. So the algorithm is identifying what carbon becomes the carbonyl carbon, and then just, counting. So don't get fooled by, distractor things that really can't get into the molecule some other way. Questions? So we're going to look at this retrosynthesis in the last couple minutes here. So here is just a summary of what we've done so far. Secondary alcohols can come from aldehydes, tertiaries from ketones. If you have a carboxylic acid in the molecule, it's going to do an acid base, so you can't have any of that. Esters and acid chlorides will give you tertiary alcohols. Capiche? So here's the thought experiment. We're going to consider a tertiary alcohol. So R1, R2, and R3 are all carbon. And so to the bottom left there, that's what we want to make. And conceptually, we want to think about what are the three pairs of electrophile, so that bears the carbonyl, and then the nucleophile, that's the organometallic reagent. So phenyl methyl ethyl. Just leave it like that. So we'll say electrophile, nucleophile. And three ways to do it. Just thought of a sort of a better way to show this. So in the first one, say we want to look at that disconnection. So the electrophile should have what functional group in it? Huh? Ketone. It can't be an aldehyde because all of the substituents are carbon. So if it's a ketone, it's got to be 1, 2, 3, 4 carbons. And carbon 2 is the ketone for a carbonyl group. So that means this part of it has to be the organometallic. Switch it up and make it magnesium iodide. So that's one route. So in the second route, we want to make that disconnection. So now we would have an aromatic ketone. And then a 2-carbon organometallic. And then the last one, we'd look at breaking the last carbon-carbon bond here. So we would have a 1-carbon organometallic. So conceptually, that illustrates the 3 ways you could make any alcohol. So if you're dealing with primary or secondary, then you can use hydride reagents because they have, they're delivering H-, or you could start with aldehydes or ketones and match up your pairs that way. Any questions? So this is what I do for a living when I'm not teaching. I look at molecules and think of ways to make them. And then the poor undergraduate souls that do research with me are tasked with carrying out these ideas. But that's what organic chemists do. They take molecules and what can we start from? When you look at these, how would you make your decision on what to do in the lab? Again, it comes down to cost and how you handle things. So we'll end there for today, and then next week we'll start on oxidation. So alcohols to aldehydes or ketones.